All right. Good morning, everyone, and welcome to APNIC eLearning web class. We'll be discussing about BGP Basic today. As you all know, BGP is a border gateway protocol that actually used to do routing in between two different network, to be specific, to different autonomous system. Okay, so in BGP discussion, what we'll be trying to discuss is all about the basic of BGP. So yeah, we'll try to sort of define what BGP is, what are the terminology that you need to be familiar with to understand BGP in a better way. And also we'll try to introduce some functional aspect of BGP, how BGP normally works. Okay, so it will give you a introductory knowledge so you can extend your knowledge further on BGP. All right. So before I move into further detail, this is what a bit of introduction about myself. My name is Nurul Islam Roman. I'm currently the senior training specialist in APNIC. As you can see on the slide, I have got interest on some topics. So if you have any question on context, you feel free to ask question anytime. All right, and when you have question, you can ask your question anytime. You don't need to wait till the end of the presentation. Just type your question on the chat box. I'll try to keep my eye on the chat box when I'll be presenting. So I'll try to answer your question as quick as I can. So when we'll finish the presentation, I'll show you an URL. That URL you can use to give us some feedback. And as we always mention, your feedback is very important because this is how we will try to improve our future e-learning. All right. And finally, acknowledgement to Cisco Systems because we use some of their materials when you develop the delivery content today. All right, so let's move on. This is what an overview that we have for today. We'll be starting with what is BGP, right? And definitely we'll try to sort of, when we define what is BGP, we'll try to sort of define it from the operator's point of view, from the engineer's point of view. And then we'll try to see some features that BGP has got. And definitely it will help you to sort of plan in which way BGP you can plan for deployment. And then we'll see what type of protocol BGP is, and what are the attributes that BGP share in terms of path vector routing protocol. Then we'll try to see some terminology on peering and transit. Those two definitions are very, very important because this is how the business process actually come into picture from peering and transit concept. Then BGP general operation, how BGP normally operates, right? And then we'll see some terminology and attributes. And then we will see some configuration template, how we can configure BGP in a router. And when you will see the template, we will use Cisco specific commands. And when you understand the basic concept and how to configure it, it's just a command, right? If you have a different platform, you just need to know the equivalent command, that's it. But the conceptually it is same across all the devices that you use. All right. Okay, what is BGP? As I said, BGP stands for Border Gateway Protocol. All right, so what is Border Gateway Protocol? If you see the routing protocol that we use to do routing for IP networks, especially the service provider network, normally we have got two class of routing protocol. One is IGP, which is interior gateway class. Other one is eGP, exterior gateway class. Interior gateway class where OSPF belongs, ISIS, EIGRP, REAP, those can be an example of interior gateway protocol, right? Or IGP. Those interior gateway protocol normally we use to do routing or to select the best path within the infrastructure, right? So when within the infrastructure of a service provider or an enterprise, when they select the best path, normally the best paths will be selected based on the actual path cost. It means which path is best in terms of delay, in terms of the link quality, right? And other factor, even the bandwidths and all that we have on the link. So that's what we call actual path cost. So interior gateway protocol normally used to select best path based on the actual path cost, right? The way we try to measure the network quality. On the other side, exterior gateway protocol, where BGP belongs, they select the best path not really based on the actual path cost, but based on the business requirement. That's why BGP is considered as policy-based routing protocol. It means to select the best path, policy is important. Path cost is not that important, right? Because path cost in a sense, the actual path cost that I mean. So say for example, from ISP A to ISP B, when traffic goes, based on the business requirement, based on the business interest, which path the network administrator would like to win, right? So this is what BGP is. So BGP is a protocol that perfectly sit for the routing in between two different network, and best path selection is more towards the business policy, not the actual best path that the way IGP routing protocol did that. All right, so yeah, so BGP is normally used to do routing in between two different AAs. Sometimes we saw BGP used within the network as well. That's what we call eBGP, right? Interior BGP. But still, the eBGP, the purpose of eBGP is to carry the external prefixes either from the customer or from the upstream, to carry it within the infrastructure. Because normally if you see in a bigger environment, when you need to connect to the internet, external routes are huge, right? Close to 500,000 prefixes if you have full BGP feed. So those close to 500,000 prefixes, if you collect on your border router using BGP, right, then how those 500,000 prefixes you will send across to the other side of your network, right? And within your network you're running OSPF. You can't send those 500,000 prefixes into OSPF so that it will be carried towards the other side of your network. OSPF cannot scale, right? So that's why we use even BGP within the infrastructure to carry the external prefixes, right? So that your routing protocol can scale. So in this situation where we need to carry external prefixes through the infrastructure, like huge number of prefixes, we still use BGP, but that is internal BGP. I'll explain those things when the slide will come. So BGP is now a de facto standard. So it was a de facto standard, but now it become almost a standard by the RFC. So RFC 4271 that explain the BGP protocol. And if you need to know more about the BGP protocol from the developer's point of view, right, then RFC would be the master document to read it through. So there are a number of RFCs that you can refer to if you need to know more about the very nitty-gritty of the BGP protocol. BGP features. What are the features that BGP has got? It's a path vector routing protocol. So what does it mean? It means when we learn any route through BGP, right? Through BGP routing protocol, when any router learn any route, the router also knows through which path the prefix came. So through which path means through which networks the path came, right? So that if the routers or if the router has got more than one path to the same destination from different source. Normally in internet, any networks are connected to multiple upstream, right? So when any networks are connected to the multiple upstream, and if you learn any destination for a particular network through multiple upstream, then definitely you need to decide which upstream is the best path, through which upstream you can send the packet sort of, in low latency, or even, in your business policy, what it permits. So when BGP learn route, it also sort of incorporate through which network the routes actually traverse to or came via. So that is what we call path vector routing protocol. And BGP support incremental updates, so which is a scaling sort of scalability features. So for example, if BGP need to sort of deal with 500,000 prefixes, and is there any change happen on your network, right? Anywhere in external networks, obviously. And for that reason, if BGP need to recalculate the whole routing table, that's not good, right? So BGP is that support incremental updates, so that when any change happen into a network, only that particular change will be propagated, so that BGP can remain sort of converge all the time, right? Unless we have a disaster into a network. So all those little changes that we have into our network can be updated incrementally, right? And in BGP, there are so many options that we have to implement the policy. So, I mean, so many in a sense, like, we have a significant number of options that we have. Using that, we can implement BGP policies. So, for example, BGP policies normally use to select the best path. So to influence the best path selection process, we use some sort of attributes in BGP, right? So normally BGP, they call those attributes. Based on that, BGP try to influence the best path selection process. On the other side, if you see on IGP class of routing protocols, for example, OSPF, they actually call those metric, right? So based on the metric, they select the best path. In BGP, it's almost equivalent to metric, but since it doesn't sort of deal with the actual best path, BGP call them attributes, right? So based on the attributes, BGP select the best path, and all those attributes that BGP has got are not considered at the same time, like one by one. So there is a sequence of all those attributes that BGP has got. If number one attributes, which in the priority number one, probably doesn't take effect, then the next one, and then the next one. This is how all those policy can be considered sequentially, right? So that's why in BGP, when you implement policy, controls or path selection control can be on the both sides. So for example, if someone tweak BGP attribute, like third or fourth attribute on the BGP path selection process, when it comes to you, you can even overrule that if you'd like. If your network situation permit that, you can overrule based on tweaking the higher attribute, right, than the one your neighbor actually manipulated. So this is how BGP attributes can be used to sort of influence the best path selection process. We can discuss those things in detail when the slide will come. And BGP support classless interdomain routing, which is very obvious now, because nowadays people don't use classful concept anymore. So since we don't have any classful addresses nowadays, class A, class B, and class C, same way BGP also support that classless interdomain routing. So if you need to advertise any route in BGP, that can be anywhere from /24 all the way up to, I don't know, /8 if you have any. But normally you don't go up to that far when you advertise prefix in BGP, especially in tier 3, tier 2 environment. So, and BGP is widely used in internet backbone. We all know that. If you see the massive internet backbone that we have nowadays, in internet backbone, when all those small networks, right, connected in the internet, they need to do routing among themselves, they will use BGP as if standard, and almost all those routers nowadays they use BGP when they need to do routing in internet. Okay, and in BGP, each small networks, if you see in internet, all those small networks, we consider them as autonomous system. So each autonomous system actually group a number of routers that belongs to the same administrative control, right? So small units or each AS is sort of a building block of a BGP routing. All right, so you can explain those things. Any questions so far? Okay, what is a path vector routing protocol? A path vector routing protocol actually used when you need to span across different autonomous systems. I tried to sort of define an autonomous system in my previous slide. So as I said, an autonomous system is a collection of routers under same routing policy and under same administrative control, right? That's what we call an autonomous system. So this is what is a sort of small unit or the building block of internet. And how we identify each building block of internet in a bigger perspective. So for each autonomous system, there is a unique number. That's what we call ASN, or autonomous system number. That's a sort of a unique number that you need to use when you configure a BGP. So when you configure your BGP with an autonomous system number, right, and when the updates are exchanged in internet, so each and every updates or the network units are identified using autonomous system numbers. So your advertisement, routing advertisement, if that traverse via your upstream to the other part of the network, right? How the other part of the network actually identify your route? Definitely you have a prefix, and that prefix has been originated by an AS number, right? So and that prefix came to the or went to the other part of the network, traversing via a number of ASN. All those AS number will be added along the path, right? And this is how the path vectors will be sort of created on BGP update, right? So as I said, right, a path vector is a list of ASs or list of AS through which the prefix has been advertised, right? And why those path vectors are used in BGP? As I said, the path vector are used, definitely first option is, or first objective is to select the best path, and the second purpose is to avoid loop, right? I'll explain in future slides what is loop. But normally what happen, if your topology that you have, so for example your network is connected to your upstream, then your upstream is connected to another upstream, right? And this is how normally in internet most of the AS, they are connected to more than one upstream, right? So there is a possibility of having a circular loop coming back to your network because you have more than one path, right? So update can go via one upstream and it traverses via the other upstream and come back to you, right? So this because you have another uplink as well. So in this situation, since in the topology of your network there is a possibility of loop, how BGP will ensure the loop will not be happening? Because if there is no logic in BGP to identify the loop, then what could happen? Your updates or your routing update can be originated and then it can go via one upstream and come via your second upstream back to you, and then these things can be repeated, that update again go to the next upstream and then come back, and you can have a loop into your network, and your path vector of the prefix path vector can be extended, can be long enough because it's just sort of looping inside. So BGP has got a logic to avoid the loop, right? So based on the AS path, BGP try to make sure there will not be any loop into your AS path. And as I said, this path vector can be used to select the best path as well. Just a simple logic that you can imagine. If you advertise any route and your route is going to the other part of the internet via two upstream, definitely from other part of the internet they select the best path based on the number of A's away. They just count how many A's away through this path and how many A's away via the other path, right? And based on that, which path has got lower number of A's along the path would be the best path. That's what the common logic in BGP. All right. So this is what an example of path vector routing. Let me just grab a pen. All right. Hello. Yep. All right. So for example, if a prefix has been originated in this AS 6461, and as you can see, AS 6461 is connected to AS 600, on the other side AS 7018. Then they are connected to AS 6337, on the other side 500, right? And then they are connected to AS 11268. And also in the middle they are connected to the other AS directly as well. So in this situation, if you see, if the prefix has been originated from this AS, it can go on that other AS and then to the next AS and then to the next AS. Right? This is how prefixes are going across. And if you see, if anyone on this network, if they would like to see the prefix can have one path via this way, other path via this way, right? If AS send that advertisement via this path as well, then you will see, if we see this path, how many A's away? 1, 2, 3 A's away. On the other side, only 1 A's away. So this is how BGP can select the path based on the path vector logic we have in BGP. All right. So any question on that so far? If not, there are some definition that we have. In BGP, we have a terminology called transit, right? What is transit? Okay, transit means, in a plain English, if any network along the path is helping to carry the traffic across from one side of the network to the other side. So the network in the middle who is helping to carry the traffic from one part to the other part is actually considered as a transit, right? And to allow that transit, to allow for the traffic to go from one side to the other side, they'll charge a fee, right? That's what we call transit. So transit normally based on some fees, right? Since you are allowing the traffic going from one side of the network to the other side, right? So that's what we call transit. Peering. Peering means, well, they're exchanging traffic but without any fee, right? How it is happening, let's have a look in here. So in this diagram, what happened? From AS 6461, if AS 6461 need to access any data from AS 6337, there is no direct connectivity in between, right? So only connectivity are there in between 6461 and 6637 via either 7018 AS or via other AS along the other path, right? So if AS 7018 allow any machine from AS 6461 to get access or to sort of browse something from AS 6337, then AS 7018 is allowing a transit, right? And definitely there will be a fee for that. Peering means if those two networks are directly connected, right? AS like 7018 and 6461, they are connected. They are exchanging traffic. So for example, he is browsing data from this AS, or AS 7018 is browsing data from AS 6461 and vice versa, right? So when you see the amount of data they are exchanging is almost equal, right? So like downstream AS, he's accessing like 10 meg of data, and upstream AS also accessing 9 or 10 meg of data, right? It's sort of a win-win for both. So what they can do, they can sort of come to an agreement. All right, I'll get data from you, you'll get data from me, right, and we'll not pay to each other. So that's what we call peering, right? Peering only works if it's win-win for both, right? And since there is no fee, that's why. What is default? Default means, well, this is one sort of transit as well, right? But the transit is wherever we need to browse, wherever we need to go, right? My default transit is this, or default path is this upstream one. That's what I mean by default. It means in this situation, right, in this diagram, if AS6461 would like to browse any content from anywhere in the world, and this is what the only connection he has got, then AS7018 will work as a default, right? Wherever you want to browse, you just go via me, right? And there will be a fee for that. In tier 3 ISPs, normally this is the case, right? They carry a default route from the upstream, and wherever they need to browse, they send the request via the upstream ISP. So that's what we call default. What is default free zone? If you see the connectivity diagram among all the ISPs, there are some big ISPs in the world. We call it tier 1, the mother ISPs, like who doesn't carry any default route. They all have got explicit routing information on the top of the, or from the hierarchy on the top of the internet. Then you'll see they don't carry any default route. So they have got explicit routing information. So there are around 10, 12 big ISPs that we have now. Those are tier 1. They don't carry any default route. So that areas or that zone where people doesn't carry, or the network doesn't carry any default route, we call it default free zone. All right. So in the default free zone, if there is no specific match, they will just discard the prefix. On the default network, like in the tier 3, if there is no match, they will send it to the default on the upstream before they discard the packet. Now we'll see an example of peering and transit. Here we go, we have a nice diagram now. So now, if provider A want to communicate with provider C, right? Then what is the requirement, or how they can do that? So for example, in the diagram, A and B can peer, so they are peering, but need transit agreement with D to access traffic from provider C, right? So what is that? If A want to exchange any traffic from provider C, then since there is no direct connectivity, A only can go to C via provider D, right? So that's why we call D is allowing transit for A. But if A would like to access any data from B, they don't need to go via any provider. They can go directly. So that's what peering, all right, if they have got an agreement to exchange traffic. So I have already defined what is an autonomous system. If I need to do it again on the slide. So as I said, an autonomous system is a collection of router under the single routing policy and same administrative control. So for example, if there is a provider X, and if the provider X has got a number of location, right, from where he provide internet connectivity or internet access to the customer, all those different locations, we normally call them POP, are internally connected based on their topology, right? And if they have got link redundancy, they might have more than one connection among different POPs. So among the POP, right, all the routers, they belongs to a single administrative control or under a single routing policy. So how among the POP they will do routing? Definitely it will be depending on an IGP protocol. They can use either OSPF or ISIs. It depends on their requirement, their choice. So when those group of routers need to communicate with an external group of networks, or external group of routers belongs to a network, single network, then those two networks are considered as two different autonomous systems. because if you see the routing requirement in between their own routers and among two different AAs would be definitely different, right? It's depending on their business policy. So an AA's autonomous system is a collection of routers, right, under the single routing policy and administrative control. Normally, if you see the operator's point of view or engineer's point of view, how they share or how they define an AAS, well, if all my routers I'm running an OSPF routing protocol, right, and with another router I'm not running any OSPF but I'm running using a BGP protocol or border gateway protocol, then we can define those are two different AAs. So whatever the routers within my networks are running OSPF belongs to same AAs, right? And other side, if I need to do any routing and if I'm not using OSPF, I'm using BGP, then this is different AAs. Okay. That's how normally from the engineer's point of view we define an AAS. How to represent an AAS? When you need to configure your BGP protocol, as I said, you need a unique number, right? And that unique number you normally get from a registry, right? So that unique number you use to run your BGP protocol, you call it autonomous system number or ASN. And that has to be globally unique, like the IP address. And the registry is the place from where you can get an autonomous system number. That autonomous system number, initially it was 2 byte or 16 bit. Since it is 16 bit, if you see the number 2 raised to 16, that can give you around 65,535 number of autonomous system number, right? But as you see, internet is growing. We already have around 50,000 AAs feasible, right? So yeah, that's why for the future growth, IETF has introduced a new autonomous system number which is double the size, right? It was 16-bit before. Now the new autonomous system number is 32-bit. So that 32-bit number normally we represent in AS plain notation. AS plain notation means it's just a sort of a plain number in 32-bit. So if you can calculate 2 to the power 32, that can give you the maximum number, which is 4.2 billion or 294 billion, which is close to 4.3 billion numbers, right? Sometimes before the community has initiated to represent that big number using dot notation, right? So it's 1.0 up to 65535.65535. That's the maximum number if we represent in the dot notation. But normally in IETF, the preferred notation is AS plain. So we better stick to the AS plain notation in 4 byte AS. Okay, BGP general operation. How BGP normally operate? In BGP, when you configure BGP, you need to configure BGP peers. Peers means the neighbors from which they will learn about the routing, right? So that BGP peer can be internal BGP peer or external BGP peer. How you distinguish between internal and external BGP peers? Well, if the peering AS number is the same AS number as your router is using, that's what we call internal BGP peers, right? On the other side, if the peering AS numbers is different than what you are using, we call it external BGP peers. So depending on whether internal or external BGP peers, normally the BGP routers or the speakers, we call them BGP speakers who speak in BGP protocol, they learn routes, right? So BGP normally learn routes from internal or external BGP peer. So when they learn route from internal or external BGP peers, it goes to the BGP table, right? So BGP table where BGP has got all the prefixes, both optimal and suboptimal. Mind it, or when you or your router is learning the prefix from your BGP peers, the BGP peers, when they will send the prefix to you or your router, they'll always send their best path, right? They might have more than one path information in their BGP table, but they install the best path into their routing table, and only the best path information they'll give it to you. If you have more than one neighbors, you'll get best path from both neighbors. Then in your BGP table, you'll have more than one path to the same destination from two different neighbors, right? Then your job will be from that to option more than one path to the same destination, you need to select the best path, and that best path will go to your BGP table, right? And then also when you have your downstream neighbors or speakers, to them you advertise your best path, not all the prefix that you learn from your neighbors. In the first case, when we discussed, we learned two path information from two different neighbors. We select the best path, and only the best path I'll send it to my downstream neighbor. That's how BGP will select the best path. And if you do some policy trick, right, to select the best path, and this is how you can send your best path by tricking the policy to the downstream. So this is how we call, you apply the policy and then you influence the best path and you send the best path to the neighbor. And this is how neighbor they'll get path information from you. All right. Okay, so in that diagram, what we have, say for example, we have an AS here, AS102 has got router E, AS100, they have got two router C and D, and then AS100 on the other side, they have got two router A and router B, right? When they communicate, or when you need to add peering, BGP normally works on layer 4, which is TCP, and port number 179. BGP works on layer 4, which is TCP, and port number 179. If you have any firewall in between to peer, you need to make sure on your firewall port number 179 is allowed, right? If port 179 is not allowed, you'll have issues, you'll have problem for the peering to be up. And as I said, BGP is a path vector routing protocol, and BGP send incremental updates. So as I said, if there is any topology change happen, those topology change information will be updated to the neighboring router using incremental update. Only that particular change will be propagated, right? And in BGP, we have got two type of BGP, internal BGP and external BGP. Internal BGP actually used to do routing within your own network. So for example, in AS100, we have got router C and router D. In between router C and D, we can use eBGP protocol to exchange route. Why we use eBGP protocol to exchange route, whereas we already have OSPF running in? Because OSPF only carry your infrastructure prefix, right, for the next hop reachability. But OSPF, you cannot send or you cannot redistribute 500,000 prefix into OSPF to carry from router C to router D, right? So to carry the external prefix collected on router C, right, which is probably 500,000 prefix in internet, to router D, you can configure an eBGP peering, right, so that through eBGP peering you can send all those path information to router D, but not redistributing those 500,000 prefix to OSPF. If you do that, your OSPF cannot scale, your OSPF cannot survive with 500,000 prefix. Alright, OSPF only carry the infrastructure. It means to carry or to make sure how from router C to router D I can go using loopback. Say for example, just advertise the loopback prefix, and for 500,000 prefix, if you send it via OSPF, then for 500,000 prefix, next stop is single prefix, a single address, which is your loopback. That loopback need to be reachable via OSPF. So that is what the basic concept of BGP. BGP terminology, as I said, in BGP we have neighbors. And what is a neighbor? Neighbor is sort of two routers in BGP. They agree to communicate among themselves, right? And in BGP, how you configure neighbor? You need to configure neighbor manually. So it means when two routers, they can ping each other, right? Either via OSPF or via static route. If they can ping each other, then you can add BGP neighbors. When you add BGP neighbor, then they create a BGP session among themselves on TCP and they start exchanging route. So to become BGP neighbors, not necessarily those two routers need to be connected directly, right? As long as there is a reachability either via static route or via an IGP protocol, then BGP neighbor relationship can be added easily. Okay, so yes, so to configure BGP peering, neighbor don't need to be connected directly. eBGP, what is eBGP? Okay, eBGP, as I said, when BGP is running in between, when BGP is running within the same AS. So for example, when you are adding neighbors, right, the neighboring routers are belonging to the same AS, we normally call it eBGP peer. And when eBGP peer they exchange route, right, the behavior, the way they will exchange route will be a little bit different than when they exchange route with eBGP peer. So what is eBGP peering then? In eBGP peering, when you configure neighbor relationship, if the neighboring router has got different AS number than your router, then that's what we call eBGP peering. When the neighboring router has got different AS number, right, then it become eBGP peering. In eBGP peering, by default we expect they are directly connected, but in eBGP peering there is a way, even though the neighbors are not directly connected, you can add peering by using eBGP multi-hop, but that is different story, but that is not recommended in the service provider network. In the service provider network, what is recommended? For eBGP peering, neighbors need to be directly connected, right? As I said, there is an exception. Even though neighbors are not directly connected, eBGP peering can be up. Any questions so far? No? Okay. All right. Now we'll see BGP attributes. What are BGP attributes? All right. Okay. As I said, BGP attributes is something that we can consider as the metric that we have in IGP or OSPF. So BGP attribute is something that BGP protocol actually carry with the routing updates, right? And when those attribute goes to the other side, when other side they'll select the best path, they look at those attributes, and from the attribute values, right, they select the best path. And as I say, BGP has got a number of attributes. So when BGP protocol will consider the attribute to select the best path, not all the attributes will be considered together, right? They will be considered in a sequence in BGP, right? So all those attributes that we have in BGP are classified into a number of class. So for example, well-known attributes and mandatory attributes. Well-known attributes are something that must be supported by every BGP implementation, right? That's what we call well-known attribute. So for example, yeah, I mean your origin, your AS path. So those well-known attributes, some of them are called mandatory, right? And some of them are discretionary. So discretionary attribute means, well, those attribute is there. The attributes are there in the BGP update, but you probably don't consider those when you select the best path, right? So that's what we call discretionary attribute. Some of the attributes are optional, and optional attributes are again in two classes, transitive and non-transitive. Optional attributes means when you send the BGP update message, on the update message you can send that attributes or you cannot send it, right? It depends, right? And those attributes are in two classes, transitive and non-transitive. What is transitive? Transitive means when the attributes comes to you, even though you don't bother what is on the attribute in selecting your best path, but since it is transitive, you can or you need to forward it to the next orders, next AS. That's what we call transitive attributes. Non-transitive attribute means if you don't use it, you just discard it. You don't need to send it to the next AS, right? For an example, aggregator, community, MED, those are optional attributes. Community is transitive attribute, right? MED is non-transitive attribute. Aggregator is also a transitive attribute. Okay. BGP, IGP model and used in ISP network. So how IGP or Integrated Protocol and BGP can be used together or need to be used together. As I said, in an ISP environment, right, we have more than one routers, like 5, 10, 20, 200, 2000 routers are connected based on how many POP you have around your country, right? So all those POPs routers are internally connected with other routers using multiple topology, right? Because of the link redundancy. So the purpose of IGP is from one side of your network to the other side of your network, how the reachability within your network will be ensured by IGP. So for example, OSPF. Normally what we do, we advertise loopback into OSPF in IGP. So that this is how we can keep the OSPF or IGP routing table short and sweet, small, right? Because as we know, if IGP table grows, then it will be difficult for us to manage it or even run the network, because if IGP table is growing, your convergence time will also grow. So if any network change happen, it will take long time for a network to converge, right? So we'll try to make sure IGP is as short as possible. And then on top of it, we use eBGP. Why we use eBGP? Because as I said, if we have a big network, on the perimeter side or on the edge where we are connected to the external network, we'll collect external prefixes. And external prefixes is depending on the customer, right? If we have 10,000, 20,000 customer, then altogether we can have 20,000 external prefixes are coming into our network. And those 20,000 prefixes or individual prefixes collected by the perimeter router, and if you need to send it to the other side of the network, then we can't use IGP for that to send it across, because then IGP will be growing because customer is growing all the time. So we have to have a demarcation. We will have BGP, like eBGP protocol running again in between those ASs, in between those POPs. There is a scaling technique called route reflectors and others, but there will be a eBGP session need to be run in between POPs. Why is that? Because when the external prefixes will be collected by the perimeter router, those external prefixes, when we send it to the other side of the infrastructure router, we don't need to redistribute it to OSPF, right? So what the OSPF is doing, OSPF is just ensuring the next hop reachability. Say for example, if router A is collecting any customer prefix, sending that customer prefix to router B via eBGP, then on router B, if you see how to collect to that customer prefix, next hop will be router A loopback. And to reach router A loopback, OSPF will ensure the reachability, right? So that's what the purpose. And eBGP will be used on top of eBGP to collect the route from the external peers. So for example, your customer, their router is running BGP as well. So from your POP routers to the customer CP router, you'll have eBGP running. You collect the external prefix. Then from that POP, right, who collected the external prefix, goes to the other POP via eBGP, not sending on to the OSPF. And when it goes to the other side, then eBGP will ensure the router who collected the prefix will be reachable. The loopback will be reachable via IGP. So that's what a service provider or ISP network need: IGP, eBGP, and eBGP all together. All right. Any question on this one? Okay. Internal BGP or eBGP. As I said, internal BGP or eBGP is our BGP peering is running with the same AS. That's what we call eBGP peering. And for eBGP peering, we don't need directly connectivity or direct connectivity among those eBGP peers. As I said, if you have 2000 routers within your network, right, all those 2000 routers are reachable via OSPF. Doesn't matter router A and router C are directly connected or not. Router A and router C might be connected via a number of other routers, right? But still, if from router A to router C we have a reachability via OSPF or ISIS or any other IGP protocol, we are happy to add eBGP peering, right? In eBGP peering, there is a requirement of full mesh connectivity. Why is that? Well, since in eBGP peering, right, direct connectivity is not required, right? Via sort of external routing protocol, if the reachability is there, we can add eBGP peering. Then there will be a question, okay, if from router A is connected to router B and then connected to router C, and router A and C are talking directly on eBGP and they exchange the route, then what is the problem? Well, if A doesn't have a connectivity with router B, then the problem is router C cannot install the route into the routing table, because when the router C need to send the packet across router B, and if router B doesn't have any route information what is talking about, then there will be a hole, right, or black hole. So yeah, there are so many issues will be happening. That's why in eBGP, all those routers, they need full mesh peering, right? So if you don't have full mesh peering, eBGP will not normally eBGP will not send the prefix learn via another eBGP peer to the other eBGP peer. So because of these issues, so what will be happening in eBGP, if router C receive a prefix from router A, router C will not send that prefix to other routers, because router C has learned that prefix from router A via eBGP. That's the default rule. If via eBGP router C learn any route, he will not forward that route to any other routers within the infrastructure or any other eBGP peer. Why? Because router C knows, well, the prefixes that I learned from router A, to let it update to router C, router B is router A's job, like to talk to him directly, right? So that's what the default behavior in eBGP. Any question so far? Okay. So internal BGP, eBGP, as I said, is topology independent, so we don't need any direct connectivity. And each eBGP peer, like router A, router D, C, B, all need to be paired with each other to have reachability to every part of the network. Normally in eBGP peering, it is recommended to do peering on the loopback address. Say for example, in this situation, every routers A, B, and C has got their own loopback. They advertise the loopback, right? And then afterward, when the peering will be added, the peering will be on the loopback address. Why is that? Because if we don't use the loopback address, if we use the point-to-point link as a peering address, then from router A to router C, if we use this point-to-point address for peering, and if the network goes down, then still router C is reachable via the other path, but since the link is down, the IP address is not reachable, right? Even though we have another path. So that's what the problem of doing eBGP peering on the point-to-point address. What we can do it in a better way, if we create a loopback on each routers, right, and then we advertise the loopback prefix into OSPF, then OSPF will never go down, right? Sorry, not OSPF, loopback will never go down, right? Even though the link is down, but the loopback address is reachable via the other path, and that is OSPF job to make sure the loopback is reachable, right? So this is what much more scalable design, much more intelligent design. Use loopback in eBGP and do peering on the loopback address in eBGP. How BGP construct the forwarding table? Well, BGP has got in process, out process, right? So when BGP learn any route, it actually takes in the in process, right? And before it takes into the in process, it checks whether there is any filter, and if the filter permits, right, or any policy filter permits, it takes into the in process and select the best path, and the base path will go to the out process, and also the base path will go to the routing table, right? So when they select the base path and put into the in table or in process, sorry, in the routing table, what they check the prefix length, right? For the same prefix, if we have more than one path, it means prefix and prefix length has to be same. Then we consider it the same path, multiple same destination, multiple path. If, say for example, you have prefix 10.0.0.0/16 and 10.0.0.0/24, those are not equal path. Those are two different paths, and it will use lowest protocol distance. So like IGP, EGP, and all AD values. Okay, constructing the forwarding table. The thing I had just explained in a graphical way. In process, will take everything, right? And if your policy permit, it accept. If policy doesn't permit, it discard, and then it goes to the BGP table. They select the best path, and best path will go to the out process and the routing table as well. eBGP peering, external BGP peering. So as I said, normally for external BGP peering, we prefer routers are directly connected. So for example, in this situation, if those two routers are directly connected, right, we can add eBGP peering. Why is that? Because in eBGP peering, normally we connect it to two different upstream, right? So if we two different upstream, if we don't use point-to-point link as our peering address, then if the link is down, then what will happen? Loopback, if we use loopback address as a peering address, then if the link is down, then still the loopback is reachable via the other path, right? And if the loopback is reachable via the other path, then BGP will not have any signaling among themselves to signal them the link is down and withdraw the route, right? So that's why in eBGP peering, we always prefer to do the peering on the point-to-point link. How to configure BGP? Well, in Cisco IOS, from the global configuration mode, what we do, router, BGP, and your process ID, not process ID, sorry, your AS number. Your AS number is 100. In this case, this number has to be unique, and that has to be a unique AS number. You can use a private AS number for that, but in that case, you cannot connect it to the internet. If you have 4-byte AS number, you can use the plain notation, or you can even use the dot notation, right? And if you want to use the dot notation, and then you can just specify the command BGP AS dot notation dot. Then it will take the dot notation all the time, and even in the AS path and everywhere it will show you the dot notation. Okay, say for example, router A in AS 100, how you configure the BGP peering? Well, the IP address that used on the interface for the eBGP peering, this is what the IP address used on our interface. On the other side, use ::1 as a .1. So in our BGP network statement, or BGP statement, what we did, neighbor 102.102.10.1. On the other side, remote AS is 101, and then we advertise the prefix, and we have got our prefix in filter and out filter here configured. What will be done on the other side? On the other side, they are using 10.1, so they will add your peering with the other side address, which is ::2. In here you see .2, and this side you will use .1. So your peering address will be .2. Remote AS will be 100, right? All right. Internal BGP peering or iBGP peering, we normally use loopback address. So that is what the loopback address, and loopback address will be the peering address. AS number 100, 100, same AS number, so BGP will identify it automatically that it is iBGP peering. All right. So how you advertised out into BGP? After you configure the peering, then you add the network statement, router BGP 100, and the network you're advertising. This is what your network address, mask your subnet mask, right? And then afterward, you have to add a pull up route into your router. So if your interface, like what are the prefix that you're advertising here, has got the exact match into your IGP table, so for example static, right, then you don't need any pull up route. But if there is no exact match, so for example on the interface level you use /27, but you're advertising /24 from here, then there is no exact match. So what you need to do, you need to add an exact match on the static with a null 0 or even on a serial interface. Then you can advertise that from the BGP. If you don't want to use the full prefix on the serial 0, because if you have more than one serial connected to different customers, then you can add it on the null 0 interface. Alright, and then afterward, when you configure it, if you use this command, show IP BGP summary, then you can see your BGP neighbors, version, AS number, message received, message sent, table number, in queue, out queue, and since how long it is up. How you know our BGP peering is up? If you see a number here, how many prefixes we are learning. Is it 0 or 1, 2? There will be a number. If you see anything other than the numbers like active, ideal, right, then your peering is not up. It has to be a number here. Right? So how you can see the BGP table? Just show IP BGP, then you can see all those routes learned by BGP, right? And there is some flag like prefix origin code I, E, and question mark. And if you see the prefix with the greater than sign is the best path. Okay, and that's what your next stop. Like to reach this destination, through which interface it will go via. And those are the example of BGP attributes. So for example, metric, local pref, where we can discuss those BGP attributes in a future presentation, because we have another module called BGP attribute and path selection process. So on that one, we can explain all those attributes. Alright, so that's the end of our presentation for today. As I said, this is what the feedback form that you can use to give us a feedback. When you finish giving us the feedback, then it will redirect you to an FTP site. From that FTP site, you can download the presentation. The presentation that I used today are already uploaded into an FTP site. You'll have access to that FTP site when you will finish that feedback. So when you finish it, then it will redirect you automatically to that FTP site. From there, you can download the presentation that I used today. I'll type that URL for you. surveymonkey.com/s/apnic-2014-0212-EL1, right? Okay, surveymonkey.com/s/apnic-2014-02-EL1. Yep, that's it. So if you use this URL, you can send us the feedback, and after the feedback, you can download the presentation slide. Is there any question? Okay, if not, then hope the session will be useful for you, and we will see you in our future e-learning session. Thank you very much.